All right, still with conservation of energy, but shifting the concept a little bit. Um, Instead of dropping something, instead of figuring how fast it's going when it gets to the bottom of a big hill, we're going to shift gears and we're going to talk about something that's skidding to a stop. We got to be in the world pre-ABS brakes, so literally just lock up the wheels and slides to a stop. If we start, like, picture maybe when you were a kid, you're riding your bike on the sidewalk and you're zooming around. As you're biking, bike is moving, the bike is going to have kinetic energy. Maybe you went up and down a hill, but we're going to keep it easy. We're just going to have you on a flat sidewalk zooming around so you've got some kinetic energy. That energy came from your body. You had to eat breakfast to get the bike moving. Maybe in the era of e-bikes, some of that energy came from a battery pack. But once the bike is moving, it's got kinetic energy. When the bike skids to a stop, slams on the brakes, and stops moving, where do all those joules go? Kind of like the car, the joules are gone. They don't go back in your body. If anything, they create a little bit of heat. The tires would be a little bit warmer. As you skid, the sidewalk would be a little bit warmer. They create a little bit of heat due to friction. When we started all this topic way back when, a few videos ago, friction and heat, these are things that physics people didn't really understand about energy. So it took a little bit while to figure out that friction could actually produce energy. It produces energy in the form of heat. So basically, when we think about our energy transfer, the energy transfer is going to be kinetic energy into energy that friction steals away. We haven't talked about the energy that friction steals away, but we can kind of build the equation. We know that energy is related to work, and we know that work is FD cosine the angle. If I made up a question about a person doing work, then I would need the force of the person. When we talked about gravity, we needed how much work it takes to climb stairs. For that, we needed, since it was the work to overcome gravity, we needed the force of gravity. If we follow that pattern, if I'm curious about the work that friction does, so for the person, we needed the force of the person. For gravity, we needed the force of gravity. If I'm curious about the work that friction does, then hopefully you can see follow the pattern here, that if we're curious about the work that friction does, we need the force of friction. Yay, luckily we did that last week. When something skids to a stop, friction kind of steals those joules away. So EK goes into E friction. Sorry, a little bit messy. We need to figure out the work done by friction, but work is always force times distance. So if I'm curious about the work done by friction, then work done by friction, oh sorry, that's terribly messy. Work done by friction is going to be the force of friction times the d times the cosine of the angle. Now the cosine of the angle is just going to be 0 degrees. Friction's horizontal, the ground is going to be horizontal. You can double check on your calculator, but cosine of 0 degrees is a perfect 1. So when something's skidding to a stop, we have kind of a new little equation. It's not going to be typed on sheets. You're going to have to kind of build this one. The 1/2 mv squared equals force of friction times d. We'll practice this a couple times. I'll show you how it works, and then we're moving on. Our classic kid on a bike. Let's say they're moving at 8. That's going to help us with the kinetic energy. They slam on the brakes and they skid to a stop, and the coefficient of friction. Oh, wait a minute. I didn't give you FF. So hopefully we remember week 2. The concept is the kinetic energy goes into the energy due to friction. Kinetic energy is always 1/2 mv squared. The energy of friction is going to be the force of friction times d. Because of the cosine 0 thing, I'm not going to worry about writing the cosine. That's just 1. But I was a little bit of a wiener when I made up this question. I didn't tell you the force of friction. I told you the coefficient of friction. Now we got to go back. We practiced it in the very first video of week 3 or week 2 stuff. Force of friction. Oh boy. Force of friction. Let's try and be a little bit neater. force of friction, we only have one equation for it. It's mu times Fn. Because this doesn't say anything about the kid being in a rocket ship or an elevator or falling through the ice, and it's going to be mu mg. So a little bit of force stuff we got to pull into our energy stuff. When a car skids to us, or anything skids to a stop, the 1/2 mv squared equals ff, but ff is really mu mg multiplied by d. This won't be on our equation sheet, but this one is kind of our endpoint for when something's skidding to a stop. The 1/2 mv squared goes into mu mgd. The m's cancel out, kind of cool. Now it just turns into a plug and chug. 1/2 of, the kid was going 8, so 8 squared equals the coefficient of friction, 0.8. The g is 9.8, and then d. We're going to solve for d. On the left, I can do a little bit of mental math. This number is 32. Multiplying by 9.8. This one, 0.8 times 9.8 is going to be close to 8, but it's a little bit less. I got 784. So one step away, divide both sides by 784, and I get d equals 4.08 when I round off to 3 decimals. All right. Same idea, but switching our concept up. What if instead of a kid on a bike, it was a car? We got to pretend it's a car without ABS because ABS changes things. But if a car locks it up and skids to a stop, if I tell you that the car goes 20 meters, we can figure out the coefficient of friction. Car's going 54 kilometers per hour. We got to convert that. Either do it like you do in chemistry class and convert one thing at a time, or if we remember, our conversion number is 3.6. Because we're going 2 meters per second, seconds are so small, we divide by 3.6. This one's fairly clean. 54 kilometers per hour is 15 meters per second. The kinetic energy gets taken away by friction. So 1/2 mv squared equals force of friction times d. If we were asked for the force of friction, we could just put our numbers in there, but we're asked for the coefficient of friction. So we have to go one step farther. 1/2 mv squared equals mu mg times d. Where that came from is ff equals mu fn, and fn is equal to mg. M's cancel out, and we're back to a plug and chug situation. 1/2 converted was 15 equals, I don't know, times 9.8 times 20. 15 squared is 225. Half of that is 112.5. Do a bit of calculator work to make sure I'm not goofing up. 9.8 times 20. Again, do a bit of calculator work, make sure I'm not goofing up. I got that to be 196 times mu. So to get mu all by itself, it's the 112.5 divided by the 196. So mu is equal to 0. If we go 3 decimal places, 574. Do the calculator work to make sure I didn't goof that up. Do the calculator work, slow down, read it over, make sure you get the concepts. And then we got one last little kind of energy to talk about, and we're done week 3.